All right. So let's talk about the Laplace transform. Now I am writing it as an integral right now. We're going to use the integral form very often. So don't be too intimidated by that. Let's just briefly talk about what this thing is going to do using an equation that we would never actually solve with it, other than to illustrate it. So suppose I have some initial value problem. And this sort of thing is far too powerful for this. This is overkill. This is like watering your bonsai tree with a fire hose. Just not the best way to do it. What happens, and you'll understand this better once we do the Laplace transform, but I want to give you an overview, is that through this integral, through a table of Laplace transforms, we'll be able to turn that differential equation into an algebraic differential equation. And there's no reason why anything that I'm writing down should make sense. This is the Laplace transform of that equation. Why? You'll see later. And then, this next step you certainly could verify. I'm just solving for the big capital X. And I would need to use some partial fractions. And we'll talk about ways of making that less painful. One way would be just to leave these letters A and B as undetermined. Right? That saves a lot of work. And the idea is that this thing, which we don't want, is the Laplace transform of something else. It's the Laplace transform of the solution. And again, don't try to necessarily figure out like, oh, why is that the case? And we'll learn that shortly. This is the thing we've been working on, which is to start with the differential equation and end with the solution. This process is a bit more roundabout, but especially if we're using a table here and a table here, which is what we're going to be doing, we'll be solving differential equations, again, without any sort of derivatives or integrals. It's a little weird, but it can be very powerful. Now again, this initial value problem is far too simple to bother. We could solve this in 1.9. We could solve it again in 4.6. We don't need this method to solve it. But we are going to look at cases where this method is very powerful, and we will want to use it. So let's get into some of the nitty-gritty details. The first thing I want to do is look at the Laplace transform of the derivative. Now, it might seem weird that we can even do anything about this. I haven't specified what the function f is, but we can. And we can do it integration by parts. This actually is a really common use of integration by parts when working with general functions, is we can take off derivatives. We're going to basically take this derivative off and put it over here, and we'll see what happens. But this is going to be my choice of u and dv. So if u is e to the minus st, then du, notice this is all in t, it's going to be minus s e to the minus st dt. And then if dv is f prime dt, then v is just f. So let's work this out. uv, so that would be f e to the minus st, 0 to infinity, minus the integral 0 to infinity of, what are we going to have? We're going to have duv, so there's minus s e to the minus t f dt. We can pull this minus s out. We're integrating with respect to t. So this is f e to the minus st 0 to infinity. And we'll have a plus s integral 0 to infinity of e to the minus st f dt. I realize I forgot some notation. So way back up here, we define this to be capital F of s. This thing, it's a function of another variable. Why? Well, this is a definite integral, so we're going to evaluate at t, but not at s. There will be an s left every time. So we'll have an expression in s. That's our transformed function. Then down here, this is capital F of s. It's not a specific function, but that's fine because we should be used to this solving differential equations, not having specific functions. What do we have here? This is, I'm going to just plug in infinity, very bad math form. All right, and we'll talk about that in a moment. All right, plus s capital F of s. So there is a restriction, it's a technical restriction that we don't have to worry about on how fast these functions can grow. It can't grow faster than this decays. Otherwise, this thing will blow up. It's not good. But we're going to assume that f grows slower than exponentials grow, and so that this will go to 0. E to the 0 is 1. That's minus f of 0 plus s fs. This is the Laplace transform of the derivative. And this is sort of part of the structure of the computational method of using Laplace transforms, is that there are no derivatives left when we're done. It's just unknown functions multiplied by stuff. So derivatives become multiplications. This is convenient for solving things. Now, we're not generally going to do all these integrals. We're going to use tables. And I provide a link in Top Hat. You can use any table you want. There's one at Paul's Online Notes, which is a website that's been around forever. And it's fine. It's good. And let me just kind of write a couple of these things, and then we'll do a couple little examples. So the number 1 transforms into 1 over s. This is the first one on the table. So how would I do that to transform -3? Well, the Laplace transform is a linear transformation. So you can factor a -3 out. The transform is 1 over s. So that's -3, 1 over s equals -3 s. All right? And this goes the other way too. So if I have something like 2 over s, this is 2 times 1 over s. And on the table online, it's the right-hand column has all the transforms. And so I find a 1 over s. I see that that's the transform of 1. So this is the transform of 2. And we're going to need to go both directions. Let's do another one. Let's do e to the at. We're told that the Laplace transform is 1 over s minus a. This one's easy enough. You could actually check it with an integral too. So what is the Laplace transform of something like e to the minus t? Well, let's look at this. This is the case where a is minus 1. So I'd have 1 over s minus 1 is 1 over s plus 1. And then conversely, if I had something like s minus 5, I'd want to think about this table. I look in the table and I see this s minus a. Oh, I have that. Or even better yet, let's do 3 over s minus 5. Well, that's 3 times 1 over s minus 5. Right? So a is 5. So this is the Laplace transform of 3e to the 5t. So this is the Laplace transform of 3e to the 5t. So, and I encourage you, well, you're going to have to look at this table because I'm going to ask you questions right out of it. And the table is going to be very helpful, but we are going to have to interpret the table to use it. Now let's talk about how we could do that to solve a little differential equation, kind of like the one I just did, or I started out with. Suppose we're solving something like this. I want to solve it with the Laplace transform. So using the table, I'm gonna navigate this using the table. We can do some practice. Let's see, where's the derivative? So number 35 on the table tells me how to do the derivative of x prime, which we just derived. It's s, capital X of s minus x naught. All right. Now, this one's actually really easy. The Laplace transform of 2x is 2 times the Laplace transform of x, which is just 2 times capital X of s. There's no table entry for that. And then this e to the minus t, well, that's one of the ones we did fairly early on. That's number 2 in the table. And that's 1 over s minus a minus 1. So then we have s capital X minus 1. That's because in this problem, the initial condition is 1, plus 2x equals 1 over s plus 1. Collecting like terms, this is capital X, s plus 2 minus 1, 1 over s plus 1. All right, so let's move the 1 over. We'll have 1 over s plus 2 plus 1 over s plus 2 s plus 1. So we can certainly go ahead and do the partial fractions specifically, but I think one of the things I'm going to have you do is just stop short of going all the way. And just leaving these here. That should save you some work. Now, these are all an example of number 2 on the table. This is an e to the minus 2t. This is an a e to the minus 2t. And this is a b e to the minus t. Plus, plus. So this means that this whole thing is the Laplace transform of a solution, which is e to the minus 2t plus a e to the minus 2t plus b e to the minus t. That's what's going on here. Now, of course, there's some specific value for a and b we could figure out just from this. But this might give you enough of the idea. You know, this ends up being like, what? This would be like 1 and minus 1. So it's not hard to do sometimes. But it does get hard later on. It gets quite a bit harder. Let's do a little one to kind of show you. So let's go back to oscillations, and let's look at something like this. So here's undamped driven motion, and let's do a Laplace transform. To do the second derivative, this is near the bottom of the table. Let's see here. So number 36, they have a separate one for second derivatives, and it's s squared capital X minus s. Oh, I need some initial conditions. Let's stretch the spring by 1 with no initial velocity. So I'll have x of 0 minus x prime of 0. I get that from number 36. And then this is just plus 4 capital X. Now sine, so we go look in the left-hand side for sine. I find one. It's number 7. It says that sine of AT under the Laplace transform is A over S squared plus A squared. And it's pretty easy going to the right. It gets a little harder going back, as you'll see. This is 1 over S squared plus 1. All right. Now I can, let's see, this is 0. And then this is 1. So I'm going to have S squared capital X minus S plus 4x equals 1 over S squared plus 1. So I'll combine like terms. Capital X, S squared plus 4 minus x minus s equals 1 over s squared plus 1. Solving for capital X, I'll have an s over s squared plus 4 plus a 1 over s squared plus 4 s squared plus 1. Now a couple of notes here. This is not resonance because there's no 2 here. If there were a 2 here, there would be a 4 here and a 4 here, and we'd have a repeated root in our partial fraction, which makes this much harder, right? But then again, resonance does require a bit more math to work out the solution. So the fact that these are different makes this easier. Ugh, sleepy. Right, so we'd have something like bs plus d over s squared plus 4, whoops, plus, I should do a c, sorry, plus ds plus e over s squared plus 1, right? So with these irreducible quadratic factors in the denominator, you have to split them up using linear factors. So just imagine now that you have to find b, c, d, and f. That's not fun. That's quite a bit of work. There's no easy bit here. So this is where I'm thinking that maybe let's not. Because even if I say don't determine the unknown constants from partial fractions, don't determine the constants, this is still a bunch of work. We're not out of the woods yet. Because this is not on the Laplace transform table. So let's go ahead and see what I mean. Well, I'm going to write this in a way that hopefully will make sense. I'm going to break things up. All right. Because I want you to kind of see how these are going to be approached. I'm going to run out of room here, I think. But I'm going to try to squeeze it all in. All right. Well, yeah, I should have written smaller over here. Why did I do this? Well, because this is in the table, or almost in the table. No, this isn't the table. This is number 8. And this is in the table. This is number 8. This is cosine 2t, and this is cosine of 1t. This is not quite in the table yet. It's almost a sine. But remember, sine of at is a over s squared plus a squared. So the numerator is the square root of this constant. So I would need a 2 here, and that's fine. Divide by 2, multiply by 2. And now this is number 7, and it's sine of 2t. This is 1 and 1, so this is number 7, sine of t. Right? And then over here, of course, this is number 8, cosine of 2t. So even without figuring out B, C, D, and E, I still have a bunch of work to do. Now I can combine, so let's write this out a little bit. So this is, I have a cosine of 2t plus B cosine 2t plus a C over 2 sine of 2t plus D cosine of t plus E sine of t. Now these aren't all independent, right? Cosine 2t, so those combine, right? 1 plus b is just some number, so whatever, it's 1 plus b cosine of 2t, and I have a sine, right? Plus, oops, those are separate. Well, yeah, anyway, so I'm thinking that, I might have you stop at this point. I'm just trying to get you to experience a little bit of the Laplace transform without getting too overwhelmed in the nitty-gritty. So I think I'm going to stop here and have you do some top-hat questions using the table. So let's do that.